Greetings, algebraites. In this wonderful lesson, 3.6, Analyzing Lines of Fit, we're going to write linear equations that model real-world data. So, my class has already asked the question, is there a relationship between one's index finger length and one's foot length? So we all measured in the class, and here's a bunch of data, and then we plotted it. This right here is just that we had 4 points in the same place, so I just made it look like it was weighted. Okay, so now, then I took a ruler and I drew my line among the data. This line, of course, is called my trend line or regression line, but it's not the best one because mine's going to be different than somebody else's, and how does it relate to all these other points? And there's a fancy formula to find it, which our calculators can do very fast, and we cannot do very fast. So that's called the line of best fit. So in a moment, we'll do that together in our calculators. All right, but now, by hand, we want to pick 2 points and write an equation in slope-intercept form of the line that I drew. So it is a little bit tedious, and so let's go ahead and attack it. First, we're going to find slope, and then we're going to substitute that into point-slope form. So choosing 2 points that look really clean, or something I can estimate really well. So notice this point right here at 6.4, 6.4, comma, and it looks like it's at 21.5. So that's a cleanish point. And let's find another one, maybe somewhere near here. Now notice this is slightly shy. If I go on the 7.4 there, 7.4, it's slightly shy. If I zoom in, we can see that it is shy of the 25 there, just barely. So maybe 24.9 right there. All right, so now we have the 2 points, and we can use these to find my slope. So remember, my super secret formula for slope is y2 minus y1 over x2 minus x1. So I'm going to substitute things in right here, starting with my y's, 24.9 minus 21.5, all divided by 7.4 minus 6.4. 3.4 over exactly 1. So there we go. Here's a nice, not too crazy slope. And what does this mean? Well, it means for every 1 inch, finger grows, your foot grows by 3.4. And my apologies, we're using centimeters down here, but the ratio still stays the same. So 3.4 centimeter of foot growth for every centimeter of finger growth. So growing 3.4 times faster. Okay, now remember that point slope form looks like this. Y minus y1 is equal to m times x minus x1. So let's go ahead and substitute some things in. Y equals, which point do we use? Doesn't actually matter. I'm just going to use the first one right here, 6.4 and 21.5. So 21.5 goes in for the y, 3.4 goes in for m, x minus 6.4 goes in here. And now to finish this up, I need to distribute the 3.4 there. So y minus 21.5 is equal to 3.4x minus 21.76, and add 21.5 to both sides. 0.26. All right, practically speaking, this is the growth rate for every 1 inch of the finger, and this is my initial, or 1 centimeter, or 1 unit, and this here is where my finger begins in the negative, which clearly doesn't make sense, but it is close to 0, which makes also sense. Okay, so here is our equation. What we're going to do is plug some into the calculator, and on the next page, we'll show you with different data on how it's done, and then we'll come back and see what my data looks like here. So on the next page, let's first ask the question, answer the question based on the scatter plot above that we did. Which of the following correlations best describes my graph? Is it a positive correlation, negative correlation, or no correlation? And clearly it's positive, because as the finger length increases, so does the foot length. And there we go. All right, so this part here, if you watch this video, then it will give you information on how to use your TI calculator. And I'm going to enter my data in to see the results here in just a few minutes. So now I entered all the data into my calculator, and here's what I got after I went through and did stat calc. So stat calc, press number 4 for lin reg, and here is what I got for this specific data. Notice I have r squared and r, which I'll unpack in a little bit, but this is my slope, 3.18, and this is my y-intercept, my b, 1.37. So that's what I'm going to write here. So my y1, or my y equals 3.18 x plus 1.37. Now, to interpret this according to this graph, it says that when a person's finger is 0 centimeters, then their foot is 1.37 centimeters long. And if you make this into a 5, that'll predict how long. So notice it's about 3 times, a little bit more than 3 times larger the foot is than the finger. Now r. So the r value that I got over there, as you saw, was the 0.758. 0.758. So I can write that in here as 0.758. Okay, now what we can do is we can actually make predictions based on this model, is that we have y1 equals that function. So I can actually enter a 7.5 into my calculator to get this. So let me show you a screenshot of that. And this is what I get. I called up the y1, again, in vars, y variables, function, enter. And then I just put parentheses. So I said evaluate the function that's stored in y1 at 7.5, and I get 25.22. So that's the approximate value right here, 25.2 centimeters long if a person's finger is 7.5 centimeters long. So let's talk about that relationship that we saw, that R value. That R value I saw was something about this, 758. So correlation. The line of best fit will have a special number associated with this. This number is called the correlation coefficient, also called R. The closer that R is to either -1 or to +1, the stronger the correlation data has. So notice here, if we have a -1 and R is -1, notice that's perfectly linear. It's a great, in fact, you would say it's an exact correlation, so that my line goes through all the data points. And the same applies here to +1. Notice the negative does not mean bad. The negative means negative slope. The negative describes the slope. It's a negative slope with a perfect correlation. Now, if we were to think about it as on a spectrum, we would say that at a -1, we would have a perfect correlation, and at a +1, we have a perfect correlation as well. Just one of them's positive, one of them's negative. Notice in 0, if we were at 0 here, we would have no relationship. In fact, that can extend all the way out here, because if we're at all the way to 0.3 or something like that, we're not really going to have much of a relationship at all. Now, at 0.4, this is a very weak, it's a weak relationship. So 0.4 negative or 0.4 positive. And at the 0.7 or the 0.8, that's where you start getting into decent or middle of the road sort of relationship. And in this region, we'd probably get into the strong. So we would say a strong negative correlation. So at above 0.8 to stuff, that we would say a strong correlation. The closer it gets to there, you would say very strong until you get to perfect. So in our situation of 0.75, we would describe this one as a decent positive correlation. Decent positive correlation. So it's moderate. All right, write the equation of the trend line in the data below, and based on the correlation coefficient, describe the correlation. So this is, you have to enter this data into your calculator. Again, you're putting this into L1, this into L2, and then you have to run through the process. So pause, do that, and I will have the answers here. All right, so now let's check the data, check your results here. After we enter into L1, L2, and then do stat calc, we end up getting this equation. My R value is very strong positive correlation. Do the same thing over here, L1, L2, stat calc, lin reg, and we get this. Notice we have a negative correlation here. That doesn't mean bad. Notice that the absolute value here is nearly perfect. So that's why I said, or you could say super strong or very strong. Very similar interpretation. All right. So what does each correlation coefficient reveal about the data it describes? If you have a 0.1, in this case, we would, it's so close to 0 that we would say no correlation. There's no relationship between the data. Again, just to show you, it's like this scattered all over the place. The bees are just hovering. They're not moving in any particular direction. No line here accurately describes something, unlike this one. A line here describes the trend that the bees are all kind of going in that direction. So a 0.1, no correlation. A negative 0.6, we would say a negative, moderate, or decent correlation. So it's not strong, but we could get some data from it, or we can use the model with some surety. Not tons, so we would just take that information with a grain of salt. All right, this should be printed on the next page, but it says, how does the line of best fit compare to actual data? So here we are. Hafiz collected data on the number of toys sold at his uncle's shop during the Great Toy Sale of 2019. So approximately how many toys were sold on day 4? So the data points are the actual data. So let's look at day 4. Here is where day 4 lives, and we're looking at this data point right there. So this data point here, and that's where it corresponds to. So how many toys? There were 35 toys sold there. Next question. How many did the line of best fit predict for day 4? So the line predicts this point right here. So that's on the line. And notice I dash over to here, and so we use that number right there. So to me, that looks like a 31. Prediction of a 31. So how far off was the prediction? So the prediction was 4 toys below, because we clearly see that there's a gap there, right here, of 4, and it's underneath. The prediction is underneath. Okay. So the difference between the actual value and the predicted value is called the residual. So residual is equal to actual, and sometimes people say observed minus the predicted. Notice alphabetical, no matter which way, the actual minus the predicted, or the observed minus the predicted. So in this case, the actual was 35, the predicted was 31, and so we ended up getting 4, a positive 4. So how do we interpret the positive 4? That means the actual was 4 above the predicted, or the other way around, the prediction is 4 below. So the positive does mean something here. So what about the residual for day 7? Go ahead and try that, pause, and then check. So the actual was about 12, as we see. This is the actual here, about 12 over there. And the predicted, based on my line here, clearly is this point right here, which is either 15 or 16. I'll say 16. So notice the residual is a negative 4. Negative 4. Or a negative 3 if you had chosen 15 right here, either one. Okay. Next, interpolation versus extrapolation. Linear models are good for interpolation, or as a verb, interpolating, predicting the missing data within the domain, but not for extrapolating. Or extrapolation. So predicting beyond the domain. So if we look at this information here, we can't really predict. The cell only went to day 8 here, so I can't really predict 9 and 10 because future is future. It's not a very good. Doesn't help very much. So we're good for looking among the data, but not beyond the data. So using model in part D of the activity, choose 2 finger lengths and predict the foot length. Interpolation value yields something, and the extrapolation. So let's look here. Again, I can't really make a prediction beyond 8. Okay? So interpolation says, in fact, I already have a point marked here, 6, 4, and 21. So I'm predicting interpolation among my data, or a 7.2, I'm predicting at a 24.5. So let's use that one right there. The 7.2, which is right here, which we're saying at a 24.25 there. So, interpolation. I'm saying that at a 7.2 centimeter long finger, it yields a foot size of 24.25 centimeters. Now, what about an extrapolation value? Well, extrapolation, and this doesn't work for a couple of reasons here. My graph goes off grid, so it's actually really hard to predict based on this. But let's see what it does. If I did attempt to say, 8.2 here, and it goes all the way to about here, it looks like it's almost at 28. So I would estimate 8.2 centimeters yields maybe a 27.8 centimeter size foot. Now, I just used my data here and my line there, although here we could have done the same thing with the actual equations from part D. All right, the last thing we're going to look at is something called causation versus correlation. Does one thing cause another? So, causation means that the first thing here makes this thing happen. Correlation simply says that there's a relationship between the two, although we don't know if so numerically there's a relationship, but it doesn't necessarily mean that one causes the other. So for example, the number of books in a home versus the GPA of a student. So if I bought you 1 million books, put it in your home, does that mean your GPA is going to increase or decrease? And the answer is no. There's no causation. One does not cause the other. So in this case, it would just be a correlation. That maybe it's true, the number of books here and the GPA, that the more books somebody has, the higher GPA. You could do that, right? In fact, some data suggests that. However, I can't just buy you books and suddenly your GPA is going to go up. That doesn't make sense. So that's not causation, that's called correlation. However, it is true that it could be the number of hours you get could actually improve something on a test here. So in this case, I would argue that causation might be a situation here. That's not always the case. You know, there are some people who don't get sleep and who will do well on a test, or the other way around, who get too much sleep and therefore don't do well. But there's probably a case to be argued that this can cause this right here. All right, you have all the information from this section. Go ahead and begin working on assignment number 4 from your textbook.